Hello, today's lesson will be on binomial distributions. I'd like you to think of that word. Binomial has two parts, bi meaning two, nomial having to do with numbers. So today we're looking at distributions where there are only two possible outcomes for each trial. We're going to start with just going over what factorials are. If you look at the box on the right, the definition is of n factorial, so the symbol we use for the function factorial is exclamation mark. So n factorial equals n times n minus 1 times n minus 2 all the way down to ending up with 1, and n must be greater than or equal to 0. In other words, n is a natural number. Please note that 0 factorial by definition equals 1. Okay. So for example, 3 factorial would be 3 times 2 times 1, which equals 6. At this point, I'd like you to give our examples a try. If you're not sure, look at the first one and then pause before you go on to try the others. So at this point, you can pause and come back in a second. All right, so you've given these a try. Let's see how you did. 5 factorial would be 5 times 4 times 3 times 2 times 1, and the answer is 120. 3 factorial times 4 factorial, so 3 times 2 times 1 times 4 times 3 times 2 times 1 equals 6 times 24, or 144. 7 factorial times 3 factorial divided by 6 factorial. You could do this on your calculator and you would get 42. Oh, that's right, 42. To do it by expansion, if we think of 7 factorial as being 7 times 6 times 5, etc., it would be the same as 7 times 6 factorial. And then simply 3 factorial at the top and 6 factorial here. And then you can see that the 6's will cancel out and we're left with 7 times 3 factorial, which we know is 6 from before. And so again we get 42. So we try the same thing with D. 22 factorial minus 21 factorial divided by 20 factorial. So if I can draw out a 20 factorial from both of my parts of my numerator, then I'll be able to cancel. So here we get 22 times 21 times 20 factorial. In other words, we're going to continue on down all the way to multiplying down to 1. And then 21 factorial is the same as 21 times 20 factorial. And we'll divide by 20 factorial. So we can factor out the 20 factorial on the top. 22 times 21 minus 21 divided by 20 factorial. So these cancel out now. And when we work out the rest, it equals 441. All right, so let's move on to today's lesson of what binomial distributions are and how we work with them. So how are each of the following the same? I'd like you to pause and take a minute and jot a few notes down as to what sorts of things you can decide how these are similar. So now you've had a chance to do that. Let's look at them together. So tossing a coin 5 times, counting the number of heads. Spin a roulette wheel 8 times, record the number of times the ball lands in a red slot. Randomly sample 100 babies born in BC on a given day and count the number of males born. Or drawing a card from a standard deck and replacing it 4 times and observing the number of aces you get. Now, you should have noticed that these are similar to what we've covered in previous lessons and that they are all discrete random variables. All discrete random variables. And to remind you, a discrete random variable is a situation where we have set numbers for our possible outcomes as opposed to a continuum of possible values. Another thing you should have noticed is that these are independent events. For instance, when we're drawing the card, we are replacing it, whereas if we had not replaced it, the next draw would have been dependent on what we drew the first time. So independent events. The third item is that they all have fixed number of repetitions. They're a chance situation. They all have fixed number of repetitions. Chance situation. For instance, we're saying how many trials we're actually going to do. 5 coin tosses, 8 spins of the wheel, 100 babies, and 4 times of drawing the card. And finally, here's what makes the binary part is that we have 2 possible outcomes in each situation. 2 possible outcomes in each case. Okay. So we'll go over this again on the next page, but to summarize on this, these are all what we call binary settings. Binomial settings. And to test whether something is a binomial setting, we will use the acronym BINS, B-I-N-S. B stands for binary outcome. It's either on or it's off. We are successful or not successful. Success or failure. I stands for each repetition being independent. Each repetition is independent. Independent. N stands for the number of repetitions. Fixed number of repetitions of your experiment. And S refers to success, so the probability of success. On each trial is the same. So you could also think of it as S for same. So I'd like you now to look at how those first 4 examples are different from these next 4 examples. So you can pause at this point as well, and we will look at each of them together when we come back. All right, so you've had a time to think about how these are the same. So if we look at each one individually, A, tossing a coin until you count 5 heads. You should have identified the fact that we do not have a fixed number of repetitions here. No fixed number of repetitions. For B, spinning a roulette wheel until the ball lands in the red slot 8 times. Once again, there are no fixed number of repetitions here. Okay. For C, randomly sampling 100 babies born in BC on a given date, count the number of males born in each ethnicity: Asian, First Nations, Caucasian, Afro-American. Now, if we were just looking at males like we did in the first case, it would be binary. They're either a male or they're not. This time, we're also looking at their nationality, so here it is not a binary outcome. And finally, D, drawing 4 cards from a standard deck and counting the number of aces you get. In this case, we did not do replacement, and so each trial is not independent. It will depend on what card you drew the last time or previous times. All right, so we are going to move on to the next page and have a look again. Just to summarize the characteristics of binomial setting, we have bins, binary, independent, the number is fixed, and the probability of success is the same. So we're now going to look at the definition of binomial random variable and binomial distribution. So for here, the count x successes, in other words, the number of successes being x in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p, where n is the number of trials of the chance process and p is the probability of success on any one given, we'll continue this on any one given trial. So n is the number of trials, p is the probability of success for a given trial. Now if I'm flipping a regular coin, the probability of success for getting heads would be 50%. If I'm rolling a die and I want to know the probability of getting a 1 versus not getting a 1, the probability would be 1/6. So there would be different values. In both those cases, they would be binomial, and the probability stays the same for each trial. The possible values of x, remember x is the count of number of successes in our n trials. So the possible values are going to be from 0 to n. We could have no occurrences. We could have all of the trials having success, and anywhere in between. So looking at our next example, in which of the following situations does the random variable have a binomial distribution? If the variable does not have a binomial distribution, indicate why. So once again at this point, pause the video and see whether you can do it. What you're going to do is look at each of our requirements as we've got listed above. Binary, independence, number of trials is fixed, and success is the same for each trial. We'll see you in a second or two, or